In this video, we begin to answer the question, what is normal? Or perhaps a better title might be information about normal curves, the normal distributions, and how to work with them. To start, though, we need to consider an introduction to normal curves and specifically get a definition. I'm going to motivate this with the following example. Suppose you roll two four-sided dice and take their sum. Create the probability distribution table and the associated histogram. Now, just to make sure we're all on the same page, let's figure out what possible sums we could have if we roll two four-sided dice. Observe that this will represent, the first die, and this will represent the outcome of the second die, and in here we have all of the possible sums. They range from 2, from rolling a 1-1, all the way up to 8 from rolling a 4-4. 5 occurs most frequently. There are 4 possible ways to get a 5. You could roll a 4-1, or a 3-2, a 2-3, or a 1-4, and get a sum of 5. So let's take this information and create the probability distribution table. So first I'm going to list my outcome, and then we're going to list the probability that that outcome occurs. Recall that there were a total of 16 outcomes, so when we consider a probability, these will be values over 16. Okay, so the first possible outcome is getting a sum of 2, and there is only one way to do so, so the probability is 1/16. The second possible outcome is a 3, and there were 2 ways, or the probability is 2/16. And we can go ahead and complete this chart. Now that we have the probability distribution table, we can actually go and create the probability histogram. And so my horizontal axis is going to list my outcomes, and my vertical axis will list the probability of that outcome. So again, my outcomes are going to range from 2 all the way up to 8. Above each of these values, we're going to list their probabilities. So above 2, we have a probability of 1/16. And above 3, let's see if that's going to be 1/16. We'll make that 2, 3, and 4/16. 3 had a probability of 2/16, and we can continue to create the probability distribution histogram. Now, what are some things that we should observe about the probability distribution histogram? The first thing that we should observe is that the area of each rectangle is equal to the probability of that outcome occurring. Observe that the width, or the base, of each of these rectangles is 1 unit, and the height is dictated by their probability. And so the area of this first rectangle right here is going to be base times height, or 1 times 1/16, and so it has an area of 1/16. The area of the rectangle associated with 3 is equal to the base times the height, or 1 times 2/16, and has an area of 2/16, so on and so forth. So again, the key first idea is that area is equal to probability. But we recall from our discussions of probability distribution tables that if you were to sum up all of these probabilities, we should get a total of 1. So if the area of the rectangles corresponds to the specific probabilities, then summing up all of the areas, or summing up all of the rectangles, should give us a total of 1. And this is our second key idea, is that the sum of all of the areas is equal to 1. Now, before I go any further, I want to just take a moment to say that this scenario right here is an example of a discrete random variable. What exactly is a random variable, and beyond that, a discrete random variable? Well, a random variable is going to be a quantity whose outcome we cannot predict. When you roll 2 dice, you don't exactly know what the outcome would be, but you know it will be one of the values of 1 through, in this situation, 4, but you can't predict exactly which one. Now, a discrete random variable is one with fixed possible outcomes, and that is as opposed to a continuous random variable. Examples of continuous random variables might be things such as the temperature outside or time, because they don't necessarily come in discrete measurable quantities. They're much more continuous quantity. Okay, so refocus. Remember, we want to give an introduction to normal curves, and we really haven't done anything except giving a probability distribution histogram. before we continue, I want to ask the question, well, what happens if we change up the problem? What happens if instead of looking at four-sided dice, we look at the standard six-sided dice? Well, this kind of gives us an idea that we're going to be looking at more outcomes. In fact, instead of 16 outcomes, we have 36 possible outcomes, and here are their sums. The sums range from 2 all the way up to 12. Now, 7 occurs most frequently, and if we were to sketch its probability distribution histogram, we would get something that looks like the following. Again, 7 occurs most frequently at 6/36 of the time, or 1/6 of the time, and 2 and 12 are the least frequent occurrence. And so we have this very nice symmetric distribution going on of our possible outcomes. This symmetry that we see exhibited both for the four-sided dice and also for the six-sided dice is not coincidence. So let's continue this example even further. Now let's consider a random variable or a quantity that is continuously measured. So for example, what about the time it takes to bake chocolate chip cookies? So again, the quantity that we're measuring is time, and it's a continuous quantity. We have a rough idea of what it might be, but we can't predict it exactly. Now, let's think about the probability distribution histogram associated with the time it takes to bake chocolate chip cookies. If you've done a lot of baking, you'll know that most cookies take somewhere between 9 and 11 minutes to bake. And so if you have more and more times in which you bake cookies, you might notice something like the following, where they take on average about 10 minutes to bake, but most of them happen between 9 and 11. This would be measuring time in minutes right here. And so instead of getting this very chunky looking probability histogram, we get something that's much more smooth as we take more and more values and as we consider a continuous random variable. In the previous 3 examples, the probability distributions have all been symmetric and fairly bell-shaped. And it turns out when we have distributions with curves that exhibit both of those properties, we give it a special name. So whenever a distribution has a symmetric bell-shaped curve, we say that the curve is a normal curve, and that the quantity being measured, this is what we called the random variable, is what we call normally distributed. So in other words, if I tell you that the time it takes to bake chocolate chip cookies is normally distributed, that means that its probability distribution would have a symmetric bell-shaped curve, or what we call a normal curve. Now, why is it important to talk about normal curves and normal distributions? This is actually an important topic because many continuous random variables, or many continuous quantities, are normally distributed. I'm going to abbreviate that with ND. And many discrete random variables or quantities are approximately normally distributed. Let's now consider the key properties of normal curves. The first property is how we got here, and that's what we've already covered. What the normal curves look like. They look like this very bell-shaped symmetric curve. The second thing that I want to talk about is their average. And we say, wait a minute, aren't there 3 types of averages? Well, not completely in this situation. The special property about normal curves is that the mean is equal to the median is equal to the mode. So in other words, there really is only one average for normal curves or variables that are normally distributed. The third concept is going to bring together the idea that we saw previously, that the area beneath the curve is equal to the probability which is also equal to the percent. Now, suppose that I do have a set of data and that it is normally distributed. I would have not just an average, but I would also have a standard deviation. When we deal with normal distributions, we will actually be working with the population average and standard deviation, so mu and sigma. And recall that one of the questions that we've asked once we have our standard deviation is, can my standard deviation tell me something about the dispersion or the spread of my data values? And in normal curves, not unlike what we've dealt with before, we actually have some of those numbers. By Chevyshev's theorem, we actually obtain the following. So consider the normal curve that we see sketched here, where we have our average mu, and then I've gone and marked out 1, 2, and 3 standard deviations both to the right, and 1, 2, 3 standard deviations to the left of the average. It turns out that within one standard deviation, so this curve isn't completely symmetric, but bear with me. Within one standard deviation of the mean, so both one standard deviation to the left and to the right, we have approximately 68% of the data values, or this area corresponds to 68%, or a probability of 68%, or the probability is 68% that we fall between one standard deviation to the left and one standard deviation to the right. If we spread out to 2 standard deviations, we obtain that 95% of the area is within 2 standard deviations, and going all the way to 3 standard deviations, we notice that almost all of the data values occur within 3 standard deviations, and that is actually quantified as 99.7% of the data values fall within 3 standard deviations of our average. Now, as we discuss these large numbers of how much is within 1 standard deviation or 2 or 3 standard deviations at the mean, it's helpful to remember the fact that this curve is symmetric. So if I have the average in the middle, that means that 50% of my data values are on the left-hand side. So I'll say that this has 50% of the area and 50% of my area is here. Likewise, if we think about this 68, then that means that the portion from the average up to 1 standard deviation away to the right would be about 34%. And you also have 34% on the left-hand side of the average. So don't forget how you can use symmetry with normal curves. So normal curves, they have 2 significant numbers associated with them, or if you have a normal distribution, your average and your standard deviation. That kind of tells you the spread of this. But when we go to solve problems, it's not going to be helpful to have an infinite possibility of normal curves. And so what we do when we work with normal curves is we actually bring all normal curves back to the golden standard, so to speak. And this is what we call the standard normal curve. Now, the standard normal curve is the normal curve for which the average is 0 and the standard deviation is 1. So it's, again, a symmetric bell-shaped curve. My average is 0 and my standard deviation is 1. And as we do examples and work with normal curves, instead of having to perform the same computations again and again and again for a normal curve with a slightly different average and different standard deviation, what we do is we will take all of our normal curves, relate them to the standard normal curve for which we've already done the most important computations. So how do I relate any generic normal curve back to the standard normal curve? Turns out we're going to be using the z-score. Recall that the z-score formula took some value, subtracted the average, and divided by the standard deviation. So what is the z-score of, say, my average, we'll say mu2? Well, that's going to be my average minus my average over my standard deviation, or 0. So this gets converted to the average of 0. What about some random point right here, say x? Well, the z-score of this value, or I'll say z sub x, is going to measure the number of standard deviations this value sits above my average. And in other words, it's going to measure exactly the same position in the standard normal curve. Since the z-score measures the number of standard deviations, a value sits above or below the average. So this video at least gives us a introduction to normal curves, but to really be useful, you need to work through some examples using normal curves and the normal table.